This short video will explain the setup for the Faraday's constant experiment. So a Faraday is simply the charge, the electric charge of 1 mole of electrons. And if we can measure the number of electrons transferred during an electrical experiment, then we could calculate the number of moles of chemical that's oxidized or reduced during the experiment. And you'll see we have a hot stir plate. Now the heat's turned off and we're stirring at about 500 RPM. On the plate we have a glass electrolysis tank and a fairly large stir bar, about 2 inches. The tank is filled about 3/4 to 4/5 full with 0.25 molar sulfuric acid. That's 0.5 normal H+ ion. In the tank on the right side you'll see a strip of copper metal. Now that copper is first cleaned by dipping it for maybe a minute in 6 molar nitric acid to clean any oxides off it. Then rinse thoroughly under the tap. Dried by dipping it in acetone, and it'll dry very quickly. Then weigh it to 4 decimal places on the analytical balance so we get an exact mass. And that copper plate is, you'll see, connected by a alligator clip and a black cable which directs it in series through an ammeter. So the ammeter is connected in series. You see the black cable going into the ammeter and the red cable coming out. That red cable continues on and goes to the positive terminal. The positive terminal of this 6-volt DC power supply. We're working on the left-hand side. Since the copper plate is connected to the positive terminal, that means oxidation will occur at the copper plate. That is, electrons will be taken from the plate into the power supply, and that means that copper plate is the anode. Oxidation will occur there, and that oxidation is the oxidation of copper metal from the surface of the plate will be oxidized, producing copper 2 ion, which goes into solution. Now we won't produce enough copper 2 ion such that you can visibly see the solution turning blue, but if we ran this long enough you would. You will notice that by weighing the plate at the end of the experiment when it's dried, there will be a mass loss, and that mass loss represents the mass of copper that's been dissolved, basically oxidized and gone into solution. The negative terminal of the power supply is connected, you can see, by a gray wire. And so this gray insulated wire, it's copper wire, it has gray insulation. The insulation is peeled away at both ends, enough to make an electrical connection to the power supply at the negative terminal, and the other end that sits in the bottom of the burette has about 2 inches of the insulation peeled away. And then untwist the copper wires, spread them out so that there's more surface area. And the bottom of that wire, the end of that wire, goes into the bottom of the burette. So it's completely immersed in acid. Now, to get the acid in the burette, we have a 25 ml burette that's mounted upside down. And get the instructor's help here, but attach a vacuum hose to the top end of that burette, the high end, and open the stopcock, and the vacuum will allow the sulfuric acid to raise, do this carefully, raise up to the 25 ml mark, and then shut the stopcock off. Right, so let's watch the video and I'll explain as we go. So we see the heat is turned off, the stir's spinning about 500 RPM. The right side of the tank contains the copper plate, which is connected by the black wire through the ammeter and then on to the power supply. Here again we see the red wire from the ammeter going to the positive terminal of the power supply. Notice the meter select switch in the middle is pushed to the far left. That's a 0 to 6 volts DC setting. And again, the gray insulated copper wire is connected to the negative terminal of the power supply. And that wire goes into the bottom of the burette. Now we'll pause it here. So I see a fairly steady stream or evolution of hydrogen gas at the copper wire cathode. You want to make sure that the wires are completely inside the burette, otherwise you'll lose some hydrogen gas to the atmosphere, and that would be a disaster for your results. You notice here the ammeter is set to the 0 to 200 milliamp position. I'm reading about 85 milliamps. There is a slight variation, and that's because the wire in the bottom of the burette is clustered a bit and is holding up some hydrogen. From time to time you see a little larger bubble being released. You'll see that as we go back to the video. Now, I want to point out to you here that we are operating this under what's called constant voltage control. So before you turn the power supply on, turn the current dial fully clockwise. In other words, you're going to allow full current to flow. Now, that doesn't mean you'll get full current. It means that the current will not be restricted. The amount of current you get is determined by the voltage you apply and the surface area of the electrodes. In this case, the surface area of the wire is the rate limiting step. The more surface area you have on the wire, the more current you're going to have flowing. I tried raising and lowering the copper anode plate, and it really made no difference to the rate because there's a lot of surface there. The restricting point is the surface area of the copper strands of the wire at the cathode. So you turn the current dial fully clockwise, making full current available. Then you start with the voltage fully counterclockwise at the 0 position, and then once you turn the power supply on, and your instructor has checked first that it's acceptably wired, turn the power supply on and gradually turn the voltage up to 5 volts, and you'll start to see around about 1 volt you'll start to see some current start to flow, and as you approach 5 volts the current will reach anywhere from 60 to 100 milliamps. So with the burette filled with liquid to the 25 mil mark, you turn on the power supply and start your timer. Now, as the hydrogen gas collects to the 24 mil, to the 23 mil, to the 22 mil, and so on, for each milliliter of gas collected, record the time, record the current in milliamps, and of course record the voltage. That should be steady at 5 volts. Using that information at the end, you can actually plot the rate of hydrogen gas being formed. And you can also plot the current, which should be a straight line, should be a flat line. When the volume of gas collected in the burette reaches the 0 mark, or is approaching the 0 mark, you want to raise or lower the burette using the burette clamp such that the level of liquid in the burette is the same as that in the tank. In that way we will know that the pressure of hydrogen in the burette is the same as atmospheric pressure, and your instructor will give you atmospheric pressure. We need the pressure of hydrogen along with its temperature and its volume to calculate the number of moles of hydrogen using Avogadro's laws. This experiment gave close to theoretical results. They were very good, meaning that there really are no other reactions competing. In other words, at the copper plate anode, we didn't have interference from the oxidation of water to oxygen. Likewise, at the copper wire cathode, we didn't have the reduction of water. We only had the reduction of H+, and so it worked out quite well. Well, I hope that was helpful and edifying.